Bismillah Rahman Rahim. Now we discuss the Lacey and Kennedy's theories, and we studied how to design the unlined canals using these theories. Now remember, these theories were developed in the subcontinent. These are not the only theories or methods that can be applied for the design of unlined channels. We have other methods that are available, but since they are not included in your syllabus, so that is why we will not study them. These Kennedy and Lacey theories, these are given in your syllabus, so we use and studied these theories for the design of unlined canals. Next topic is lining of irrigation canals. Canal whose prism has been protected with impervious material or nearly impervious material, mainly to stop seepage through it, is called a lined canal. Lining of canal means that the earthen surface of the channel is lined with a suitable unerodable lining surface such as concrete, tiles, asphalt, etc. Now, necessity, lining of canal is necessary to minimize the seepage losses in canal, because we provide impervious material or nearly impervious material. You can see here for the sides, bottom, so it will minimize the seepage losses. To increase the discharge in the canal section by increasing the velocity, because in this case less resistance to flow will occur, so the velocity will increase, and you can see that a discharge that is equal to area into the velocity. So when velocity increases, discharge will increase. To prevent erosion of bed and sides due to high velocities. So if the water is flowing with high velocity, this lining, it will prevent erosion of the bed and sides of the channel section. And to reduce maintenance of canals. This lining, it helps in reduction of maintenance costs. So these are the various factors that necessitate the lining of canals. Advantages of canal lining. Although the cost of construction of a lined canal is many times greater than that of unlined canal, yet the advantages of lining are so obvious and significant that construction of a canal with lining becomes financially feasible. You can see that the initial cost of providing the lining for the irrigation canal, this is huge cost, but the advantages of lining are so significant that construction of canal with lining becomes financially feasible. The main advantages derived by canal lining are: the lining of canals prevent seepage loss, and thus more area can be irrigated by the water so saved. The cost of irrigation is therefore reduced. The lining of canal is an important anti-waterlogging measure. So as we discussed in previous lectures, that when we have unlined canal, there will be seepage losses, and this water can join the water table in the area, and it will raise the water table. And if the water table raises to the root zone or intersects the ground surface, so this is known as waterlogging. And we already discussed that if plants, they need water as well as aeration in the root zone. If there is no aeration and the pores of the soil are filled with water that is completely saturated, so it will have adverse negative impact on the plant growth, and eventually the plant will die. So this is waterlogging. So because the lining of canal prevents the seepage, so that's why lining of canal is an important anti-waterlogging measure, as it reduces seepage to the adjoining area. The lining provides a smooth surface. The rugosity coefficient therefore decreases. Clear? So we already studied in the Manning's formula, we have V in SI system of units. It is 1 divided by capital N, small n or capital N, commonly used in the irrigation books. So we write down capital N. We have this hydraulic radius 2 by 3. And we have the longitudinal slope 1 by 2. So you can see here that if rugosity coefficient, roughness coefficient, or Manning's roughness coefficient, Manning's N, so if this reduces, then what will happen? Velocity will increase. So the resistance to flow also decreases, and hence the velocity of flow in the lined canal increases. The increased velocity minimizes the loss due to evaporation, because water will flow quickly from the start to the end of the canal, so it will have less time to stay in the canal, and thus evaporation loss will reduce. The increased velocity helps to provide a narrow cross section for lined canals. You can see that we have Q is equal to AV. Now from here, area that is equal to discharge by velocity. So if velocity increases, then area should decrease. So the increased velocity helps to provide a narrow cross section for lined canals. A higher velocity prevents silting in the canal, because silting will occur when the velocity is less. So silt will get a time to settle down. But if the velocity is more, silt will not get time to settle, and higher velocity prevents silting in the canal. Lining reduces maintenance costs and possibly of bank breaching due to increased stability of section. Lining of canal prevents or reduces weed growth. Weed, unwanted plants, useless plants that normally grow in the soil when water is available. So lining of canal will prevent or at least reduces the weed growth. Canal lining prevents water to come in contact with harmful salts during transit, because the water flows from the source to the agriculture fields. So canal is kind of a transit. So in the canal, if it is unlined, this water, it will come in contact with the soil, and the soil can contain harmful salts. So these salts can be dissolved in the water, and the water will carry these salts to the agricultural fields. So canal lining prevents water to come in contact with harmful salts during transit. We also have certain disadvantages of canal lining that we should understand. The canal lining has certain disadvantages. Canal lining requires a heavy initial cost. Lining being permanent, it is difficult to shift the outlets very often. You see that when we have unlined canal, outlets where the water goes out from the canal, outlets we provide to supply water to the individual fields, agricultural fields, to the individual farmers through these outlets. So if lining is provided, then it becomes difficult to shift the outlets very often. It is very difficult to repair the damaged lining. A lined section is without a berm. This we discussed in the previous lecture. The additional safety provided by the berm for vehicular and pedestrian traffic is therefore absent in a lined canal. So these are certain disadvantages of canal lining. But however, the advantages are more, and that's why financially this canal lining is feasible. So we discuss types of canal lining. Various types of canal linings which are commonly adopted are divided into two broad categories. A, we have hard surface linings. These include canal lining, shotcrete lining, brick lining, asphalt lining, boulder lining. And the second category is earth type linings. We have soil cement lining, compacted earth lining. Now, these are the types of canal linings which are commonly adopted. We have other types of canal linings also beside these that you can read in the textbook or books on irrigation engineering. So we will briefly discuss these types of canal linings. But in addition to these, we have some other types of canal linings also. So concrete lining, best suited for main canals. Concrete lining has high initial cost, but it has long life and minimum maintenance cost. A thickness of about 5 to 15 centimeter, that is the thickness of the canal lining, this thickness. 5 to 15 centimeter and stable side slopes between 1.5 to 1 to 1.25 to 1 are adopted. We have this Ghazi Barota hydropower project. You see that is the power canal. It holds the record for the biggest concrete lined channel in the world. This is a concrete lined canal, power canal, Ghazi Barota. So this is a canal which runs from Ghazi to Barota. And their head is available. We have the powerhouse, 5 Francis turbines, 1400 plus megawatt of electricity that is generated. The channel is 51.90 kilometer long with a concrete lining and design flow of up to 1600 cubic meter per second. At a water depth of 9 meter, this is the full supply depth. It has a bottom width of 58.4 meter. The power channel has a nearly contour alignment. We studied the classification of canal based on alignment in the previous lecture. So the power channel has a nearly contour alignment with hills on the left side and the land naturally draining towards the Indus River on the right side. So the design flow, that is 1600 cubics, the longitudinal slope, that is 1 in 9600, length is 51.9 kilometer, Full supply depth is 9 meter. The bottom width of the channel 58.4 meter. The side slope 2 to 1, and the thickness of the lining, that is 135 millimeter. So this Ghazi Barota hydropower project holds the record for the biggest concrete lined canal in the world. This is according to this source. This is the WAPDA website. So if you go to this source, you will find this information written there. This is a video. You can see here we have the concrete paved machine. This is concrete paver. Next we have shotcrete lining. So it is a cement sand mortar, 1:4. The thickness of this type of lining varies from 2.5 to 6.5 centimeter. Wire mesh reinforcement is clamped to the channel surface before applying the shotcrete. You can see here the wire mesh. It is clamped to the channel surface before this cement sand mortar that is provided under pressure. You can see here this nozzle, and under pressure it is supplied this mortar here. So this is the shotcrete. This shotcrete lining, it is convenient for lining small sections, for repair of old linings, and for placing linings around curves or structures. You can see here this is shotcrete. This is another video. This is the cement sand mortar. Next we have brick lining. So it consists of a single or double layer of brick masonry. The size of brick is restricted to 30 by 15 by 5 centimeter for convenience of handling. It is hydraulically as efficient as concrete lining. In case of failure, repair can be done easily. Brick linings are by far the most widely used lining in Pakistan. This is according to irrigation book. Asphalt lining. Controlled mixture of asphalt and grade aggregate mixed and placed at a high temperature of 200 degree centigrade. It is convenient with a 30 centimeter layer of earth. It is covered with a 30 centimeter layer of earth material for a protection. The mix can be placed with a machine like that of concrete. Boulder lining. Suitable where stones of required specification are available in abundance locally. Used for lining the earthen canal cross section. To reduce the resistance to flow, because you can see here boulders are used. To reduce the resistance to flow, a 20 to 25 millimeter thick cement plaster is provided as a finishing surface. So this is boulder lining. Next we have soil cement lining. Soil cement linings are constructed with mixtures of sandy soil, cement and water which harden to a concrete-like material. The cement content should be minimum 2 to 8% of the soil by volume. Compacted earth lining. So compacted earth lining, we have soil graded to obtain the required characteristics and containing enough fines so as to make it impervious, is thoroughly compacted at optimum moisture content. Thickness of lining varies 30 to 90 centimeter. This type of lining is used where suitable soils are available. Next topic is maintenance of irrigation canals. After the construction of irrigation system in an area is completed, it becomes essential to maintain it for its proper and efficient functioning. There are various reasons due to which a canal may cease, stop to function efficiently. These are silting of canal, breaching of canal due to weak banks, weed growth, growth of plants, unwanted plants in the channel, overflow of canal banks. So these are the various reasons due to which canal may stop to function efficiently. So we discuss them. Silt removal. When the silt is deposited on the bed and sides, the capacity of the canal reduces. It is better to exclude silt by providing silt excluder and silt ejector. So these are the measures that are adopted at the canal. This diversion works we will study in detail. That is the next chapter, diversion head works. So we have the silt excluder and silt ejector. So these should be provided to exclude or at least reduce significantly the silt inflow into the irrigation canals. The following measures are adopted to remove the silt. We will study in detail in the next chapter, silt excluder and silt ejector. The following measures are adopted to remove the silt. These are the various methods: flushing, silts covering fleet, bundle of thorny bushes, iron rakes, reduction of area of flow, stirring of silt by water jet, dredging, and excavation. So the detail of each of these methods is available in the book, that is Irrigation and Water Power Engineering by Pumia. You can study the detail of each of these methods. I will discuss a few in this lecture. So we have flushing. Flushing of the canal with clear water will lift up deposited silt. Absolutely clear water should be used for flushing, but if this is not available, then the water which contains minimum quantity of silt should be used for flushing. In one way, we can remove the silt from the canals. Another method is stirring of silt by water jet. A pump fitted with a pipe and nozzle is placed on a barge. Barge is a flat-bottomed boat. Flat-bottomed boat. So a pump fitted with a pipe and nozzle, the high velocity jet is directed to the bed of the canal channel to stir the silt and prevent silting. Excavation. The silt deposited in a channel is cleared off by manual labor. Another way, using manual labor, we can clear off the deposited silt. This method is quite costly as it requires recurring expenditure. Because, for example, every year, then you have to hire the labor to clear the silt. So it has a recurring expenditure that is coming again and again. This method is generally adopted for silt clearance in distributaries and miners. The silt must be deposited clear of the channel. It means that you remove the silt, then it must be deposited away from the channel, not, for example, on the banks of the channel, so that it does not find its way back to the channel. So this is how we can remove the silt. But you see the silt or other material that is placed on the bank, it should be removed so that it does not find its way back into the channel. And this happens, you might have read in the news in Punjab, they have the Bal Safai Mohim. So that is, the silt is removed from the canals. Weed control. So water weeds are unwanted plants that grow abundantly in water under certain favorable conditions. So where we have silt or soil available and water, so naturally plants will grow in that environment, unwanted plants. So they tend to reduce the discharging capacity of channel by reducing the channel section and velocity of flow. So when we have these plants growth in the channel, definitely the channel section is reduced and it will offer resistance to the flow. So discharging capacity of the channel, that is reduced. The silted canals provide excellent base for weed growth. Weed removal may be done by plucking them by hand and burning them when canal is dry. Next is strengthening of canal banks. To prevent breaching of the canal bank, it should be strengthened properly so that valuable loss of irrigation and property is prevented due to breaching a canal section. There are different methods of strengthening a canal bank. So these include external silting system, internal silting system, and formation of bank berm. Again, the detail of these methods is available in the textbook. I will explain one of these methods. So internal silting system. Sometimes when a canal reach runs in filling, the banks are subjected to water pressure. To avoid damage, the banks must be given extra strength by increasing their sections. Favorable conditions are created to cause silting internally. Now, in this method, you see this can be applicable to new channels only. Because in the old channel already designed for the given discharge, if we allow the silting, it will interfere with the discharge carrying capacity. So these favorable conditions that are created to cause the silting internally, how sufficient wider section is provided and a part of it later gets silted, forming the additional bank. Such a method is possible only for new channels. So you can see here that sufficient wider section will be provided. So we will allow the silting to take place. Internal silting method. So this silting is intentionally allowed to take place, and this can result in this additional bank. So it will provide stability to the original embankment of the channel. So this is possible for new channels because we will provide provision for this silting. To accelerate silting, this is one of the method available. It's not that we always use this method, but this is one of the option available for strengthening of canal banks. To accelerate silting, low submergible spurs projecting from the banks into the channel may be constructed. So spurs we will study in detail in the next chapter, diversion headworks. So spurs are nothing but these are just projections that are constructed. For example, we have this projection. These are constructed of materials. It can be temporary, can be permanent. Clear? So we have these projections from the bank of the canal or river. So what happens is that the water, it comes and it strikes this bank. So it will cause erosion. So the purpose of these spurs, these are known as spurs. These are just projections. So what will happen that the water will come here and then it will try to move this way. So this way the impact of the water on the banks, that is reduced. Clear? This will be then the direction here. So when here the water will reduce the flow velocity, the silting can take place. So that is why to accelerate silting, low submergible spurs projecting from the banks into the channel may be constructed, just to facilitate the silting. Clear? Canal breaches. Canal breach is an opening or a gap developed in the canal bank due to erosion of some portion of the bank. It is an opening or gap that is developed in the canal bank due to erosion of some portion of the bank. When once water starts flowing out of such breach, it starts becoming deeper and wider. Unless remedial measures are taken to plug the breach, to close the breach. You can see here, these are canal breaches. These are opening or gap that is developed in the canal bank due to erosion of some portion of the bank. And you can see here that when these canal breaches are developed, the water can overflow and the adjoining areas can be flooded with the water. So what are the reasons for canal breaching? This can result due to defective design and construction of the bank. Defective design or construction of the bank, it can result in development of canal breaches. The canal bank is not strong enough to resist water pressure and a breach occurs. Breaching due to exposure of saturation gradient, this we already discussed in the previous lecture. The soil particles on the outer slope are dislodged and flown away along with the seeping water. A cavity is thus formed in the bank, which ultimately develops into a breach. Breaching due to rush of water through the rate holes. Shories. Shories mean lying near the shore. So we have the rate holes that are commonly there in unlined canals. Clear? So breaching due to rush of water through the rate holes. So the rate holes, that is one of the reasons that can result into canal breaches. Can be for lined canals also if the material is not strong enough. Piping near downstream toe may ultimately cause subsidence of canal banks, settlement. And a willful cut in the canal bank, either for unauthorized irrigation, somebody make a cut in the canal to take the water from the canal, unauthorized, illegal, or for allowing the flood water to get into canal to save an area from submergence. So these are the various reasons that can result into canal breaches. So now when the canal breaches occur, how we close them? Closure of the banks. Immediately after a breach occurs, the canal discharge should be diverted to a nearby escape channel on the upstream side, because we have to dump the material here to close this breach, so there should not be water flowing in the canal. So the water can be diverted to a nearby escape channel on the upstream side, or another option is the canal should be closed from the head to stop the outflow completely. But this second option, many times it is not possible to close the canal from the head, as the irrigation of the area in between may suffer. So the head may be far away, and in between the water may be supplied to another irrigation area, so that could be affected. In case of small miners and distributaries, a breach may be closed by dumping huge quantities of earth simultaneously from both sides of the gate. So if we have miners or distributaries that carry small discharges, we can put the material from both sides instantaneously, from this side as well as the other side, and quickly close this breach. In case of bigger canals such as branch canal, which carry huge discharge, the above procedure cannot be adopted. Reason is the discharge from such a canal is huge and may completely wash off the dumped soil. So if the discharge is more, the water is not completely stopped, then it can wash off this material. Because it is loose, we have to compact it properly. So this is suitable for minor and distributaries, but for bigger canal, this method cannot be adopted. So what we have to do? In such a case, it is necessary to first of all reduce the flow through the breach. This should be done by driving a double line of stakes or wooden piles, bellies, in the opening of the breach. What is happening in this case? This is now the canal, big canal. So this is now the breach opening. What we have to do, first of all, we have to provide a double pile line. This is one line here, and then another line here, and in between it has to be filled with material. So double pile line first we have to provide to reduce the flow of water first through this breach. So double line of stakes or wooden piles that is provided. The space between the pile lines is filled with planks or bushes, etc. The filler material can be secured by placing sandbags on the top. So you can see here on top, it is filled with bushes, etc., planks, bushes, etc., and then on top, sandbags can be provided for stability. The idea here is to reduce the flow of water. If the breach is very wide, another line of defense may be provided. This will reduce the inflow from the breach. Collect a sufficient amount of earth on both sides of the gap. The earth collected should either be from spoil bank nearby or from borrow pits. We discussed this in the previous lecture. This earth material is then dumped up instantaneously from both sides of the gap to form a ring bund on outer side. You can see here that these are dumped simultaneously from both sides to make a ring bund. This is a ring bund on the outer side, and then it will continue. This hole we have to close. So ring bund on the outer side. The opening is then properly filled with the suitable earth in layers, each being properly compacted. And the bank so formed is inspected carefully for few days to watch its proper function. So it should be carefully watched for a few days so that it is functioning properly. So this is how we have to close the canal breaches. maintenance of irrigation canals. Next, we discuss a design of lined canal. Although this is not in your syllabus only design of unlined canals. So design of lined canal is not in the syllabus. The reason is that you studied the course of hydraulics. And in hydraulics, you studied there about the Manning's formula, Chesy formula, and you studied about the open channel flow. So those concepts are actually applied in the design of lined canals. But anyhow, here I teach again briefly to refresh your memory how to design the lined canals. Clear? But remember, this is not in your syllabus of irrigation engineering course. Canal cross sections, generally two types of lined canal sections are adopted. We have triangular shaped or curved channel and trapezoidal shaped or flat bottom shaped channel. The side slopes are so selected that they are nearly equal to the angle of repose of the soil. You see, you study geotechnical engineering. When we dumped a soil, for example, let's say here I dumped a soil. So you can see here that for this soil material, this slope, it will be stable. Stable means that the material will not break away and fall down. But if, for example, I provide this slope, then what will happen? The material can fall down, roll down. It means that this slope, this is unstable. So the maximum slope which can be provided and it is still stable, this is the angle of repose. So the side slope so selected, they are nearly equal to the angle of repose of the soils. Why? So that no earth pressure is imposed on the lining. Because if it is steep, this earth, it will become active. So the reason is that it is so selected, the side slopes, that no earth pressure is imposed on the lining. We have guidelines for this, how you select the side slopes. The corners are rounded off to improve the hydraulic efficiency. What we mean by this? You see that we have this triangular channel, as you already studied. Now in this triangular channel, this is here, this is the side, and then the corner, it is rounded. So this will be the channel here. The reason is to improve the hydraulic efficiency, because you already studied in your hydraulics course. You see the wetted perimeter, it is reduced. So it will then carry more discharge, because you see that we have the formula for the discharge, Q is equal to AV, and V from the Manning's formula in SI system of units, this is 1 by N into R 2 by 3, and we have S 1 by 2. So you see that R, this is actually equal to area divided by wetted perimeter. So now when wetted perimeter is reduced, hydraulic radius is increased. And hydraulic radius is increased, discharge is increased. This is what you already studied in your hydraulics course, best hydraulic section or most efficient hydraulic section. So this is what is written here, that the corners are rounded off to improve the hydraulic efficiency. Triangular section is adopted for smaller discharges, as it is best discharging section. For higher discharges, trapezoidal section may be adopted. If the limiting velocity, that is the permissible velocity, that will not cause silting, scouring. We have lined canal, so silting. If the limiting velocity is taken as 1.8 meter per second, then the circular section can be adopted only if discharge is less than 85 cubics. This is written in book by Gerg, Irrigation and Hydraulic Structures by Gerg. This is written there, a guideline just in the design of lined canals. So we have triangular shaped. This is a triangular shape. You can see the edges are rounded here. Triangular channel section. The side slope Z to 1, and this is the full supply depth for the design discharge. So the bed is circular with its center at the full supply level and radius equal to full supply depth D. The sides are tangential to the curve. This is a table which can be conveniently used. For example, you see the sectional area for side slope 1 to 1. This is the equation. For 1.5 to 1, this is the equation. For 1.25 to 1, this is the equation. These equations can be conveniently used when we solve the problems. If we have other than these side slopes, then you have to develop separate equations for that. The second one is trapezoidal shaped or flat bottom channel section. Trapezoidal channel section. So we have the bottom width. The horizontal bed is joined to the side slope by a curve of radius equal to full supply depth. You can see R is equal to the full supply depth. The edges are rounded. Again, we have this table for trapezoidal channel for slope 1 to 1, 1.5 to 1, 1.25 to 1. These equations can be conveniently used. Otherwise, we can develop our own equations. You should be able to do that. But this table can be conveniently used, clear, for these given side slopes. Other than that, then you have to develop the equations to calculate the sectional area, wetted perimeter, etc. So, canal cross sections, how we design. So in order to design a lined canal section, the following data is required. That is the discharge, rugosity coefficient N, longitudinal slope, side slope, and the limiting velocity V. From where limiting velocity V will come, guidelines are available that I will discuss shortly. So the procedure for design of trapezoidal channel is given below, because we discussed the formula there for trapezoidal. The same procedure applies for triangular. So step number 1 is knowing the limiting velocity V, rugosity coefficient N. From where this N will come, actually I teach this in hydraulic course, how we calculate this rugosity coefficient N, Manning's N, clear, for various channels. So there is a procedure available. So you might have studied in your hydraulics course. I teach in hydraulic course. Longitudinal slope S, calculate the hydraulic mean depth R using the Manning's equation. So this is the Manning's formula for MKS system and for FPS system. Now limiting velocity we consider, slope is given, the rugosity coefficient is given. So R we can calculate, the hydraulic radius. There can be various procedures for, you see, the same concept but different ways of designing the lined canal. This is one of the way given in the book by Pumia. So more or less the same concepts that you have studied in hydraulics, the same concepts are applied here. Not significant changes, clear? So we have the velocity, the discharge is given, we can calculate the area of the cross section. Now we can calculate the wetted perimeter of the section using this formula here. Area is known, R is calculated in the first step, so wetted perimeter we can calculate. For trapezoidal shaped channel, area of cross section can be calculated from these equations. You can see the derivation of these equations in the textbook. For area A and the wetted perimeter P for trapezoidal shaped channel. Since A and P are known, A is known, P is calculated here. So the only unknown is this B and D. You can see here B is unknown and D unknown. So two equations in terms of two unknown we can easily solve. So the values of width B and depth D can be computed. So this is the procedure for the trapezoidal shaped channel. For same for triangular shaped channel, just these are then the equations you need to use. For triangular shaped channel, then this is the area A and this is the wetted perimeter P. Now, guideline for value of Manning's N for lined channels. You can see here cast in situ, in situation, concrete trowel finish. So the values of N 0.015 to 0.018, cement plastered masonry, this is the range, PCC slabs or tile, this is the range, values of N, brick lining, this is the range, this table is available in your textbook, split boulder lining, this is the range, and round boulder lining, this is the values of N. And the limiting velocity, the permissible velocity, so you see depends on the type of lining. For cement concrete lining unreinforced 2 to 2.5 meter per second. If you want to use greater velocity, say 3 meter per second or greater, then it must be reinforced. So cement concrete lining unreinforced 2 to 2.5 meter per second, permissible velocity can be considered. Burnt clay tile lining 1.8 meter per second, boulder lining 1.5 meter per second. So these are guideline values, clear? So let us try to solve a problem, design of lined canal. The various steps that we discuss. Design a trapezoidal shaped concrete lined channel to carry a discharge of 350 cubics at a slope of 1 in 5,000. The side slope of the channel are 1.5 to 1. 1.5 to 1. The value of N may be taken as 0.014 and assume the limiting velocity is 2 meter per second. So let us design this trapezoidal lined canal. So again, we have step-by-step procedure. So we have step number 1. We have the Manning's formula. So we have this Manning's equation. Now take care of the system of units. So we have V is equal to 1 by N, R 2 by 3, and S 1 by 2. So now in this equation, only unknown is R. So plug in the values, we can calculate the hydraulic radius R. So R is equal to 2.79 meter. 2.79 meter. Now we have this velocity that is given and the discharge that is given 350 cubic meter per second. So step number 2 is we can calculate the flow area. So we calculate the area. So A, that is equal to discharge by velocity. So the discharge is 350 and the velocity that is 2. So area A, that is equal to 175 square meter. Square meter. Now step number 3 is wetted perimeter. Step number 3, we calculate the wetted perimeter. So P, that is equal to A by R, that we have calculated both in step 1 and step 2. So this is 175 and R is 2.79. So we calculate this wetted perimeter. This comes out to be 62.72 meter. 62.72 meter. This is the wetted perimeter. Now we have the area and we have the wetted perimeter. So step number 4 is to calculate the bottom width and the depth. So we calculate the bottom width and the depth. Now for this we have the equation, we have trapezoidal section. So for trapezoidal section, the formulas are that A is equal to B into D plus we have D square into theta plus cotangent theta plus cotangent theta. And for the wetted perimeter, this is equal to B plus 2D. These formulas are written in the design steps. Theta plus cotangent theta. Now from where theta and cotangent theta values will come, you see that we have this as the trapezoidal section. So we have this as the side slope. This is Z and this is 1. Clear? So if I increase this, you see that this is the slope. This is Z. This is 1, this is that theta, and this will be same as this theta. These are alternate angles, clear? If we have this is the water surface, this will also be theta. Now this z is how much? It is given 1.5 to 1. So it means that this z, this is 1.5. So now we have tan theta, that will be equal to 1 divided by 1.5. You can easily calculate theta. So theta will be equal to 33.69 degree. 33.69 degree. But this theta is in radians. So you can easily convert it into radians. So this will be equal to 0.59 radians. 0.59 radians. Clear? Now this you can put here 0.5. Cotangent theta, this is just the inverse of theta, this tan theta. So cotangent theta, that will be equal to 1.5. So now in this theta and cotangent theta, we can replace with these values. So we have this A area we have already calculated. So this is equal to 175 into BD that we have to calculate, plus we have D square, and we have theta that is 0.59, plus we have cotangent theta that is 1.5. So let's say this is equation A. Similarly for this P, this is 62.72 . This will be equal to B plus and you multiply 2 with this. So when you multiply 2 with this, what we will get is 4.18. So this is equation number B. Again, we have theta plus cotangent theta. So this is 0.59 plus 1.5 multiplied by this 2. So 4.18. Now we have two equations in terms of two unknowns. So you can easily solve. I will just, you see here from this equation here, we can have B is equal to 62.72 minus 4.18 times D times D. And now put this equation in the above. Put this here in equation A. So the only unknown will be D. That we can easily calculate. So D will be equal to, you just solve. I will write down the value here. D, you will get two values. One is 26.89 meter, and another value is 3.11 meter. Why? Because we have quadratic equation, two roots. So this is not feasible. This is feasible value for the depth of water, 3.11 meter. Now this you can put here in this equation to calculate the width B. So we have this D equal to 3.11 meter, and bottom width of the channel, that is equal to 49.72 meter. So we have this as now the channel. We have this as the depth, full supply depth for the design discharge. This is the bottom width B, and the side slopes Z to 1. And remember, in all the cases, we have to provide the freeboard. So this is the freeboard, and we already discussed in the previous lecture that the freeboard that depends on the discharge, and we discuss it in detail, the table based on the discharge, that how much freeboard we have to provide. So remember, in all the problems for the channel design, we have to provide this freeboard. So this is a brief discussion about the design of lined canal, although it is not in your syllabus, but I discuss it just to refresh your memory. But remember what you studied in hydraulics course. So that is the procedure that we adopt for the design of lined canals. Clear? Similarly, you already studied in your hydraulics that the properties of best hydraulic cross section are most efficient channel section. So you see, for trapezoidal, half of a hexagon, rectangle, half of a square, triangle, half of a square. So these are the conditions for most efficient channel sections. If we have trapezoid, for rectangular, these are the conditions for most efficient channel section. For triangular, these are the conditions for most efficient channel section. If in the design of lined canal, it is not asked that you design for best hydraulic section, you follow this normal procedure that we adopted here. You follow this procedure. But if it is asked that you design the best hydraulic cross section for the canal, lined canal, then you have to incorporate these in the design procedure. So you have already studied about this in your hydraulics course, so I briefly discuss these things here. And finally, you see that this is a case study from Pakistan. You see the advantages when we construct a canal.
So you can see the advantage when we construct a canal.